everyone, my name is Alexandre and this is Nuno, and we are here to present the technical pitch of our team, LxUS. Starting by giving you all a general view of our equipment, it involves three main components. The first is a solution of gold nanoparticles whose function is to bind to adalimumab. The second is a laser in signal transduction that are the main components of our detection system. The third is an Android application for a friendly user interface that makes our biosensor more than just a common equipment. So, how does it all work? First, one can download the app into their smartphone and then pair the smartphone with a biosensor using a Bluetooth connection. Following this, one can pipette the sample into a cuvette already containing a gold nanoparticle solution. The final solution should be then mixed by inversion, and then the cuvette should be correctly placed into the holder. Following this, one can close the equipment and wait 10 seconds. After the 10 seconds wait, we can initiate the analysis and check the results in our app. The gold nanoparticles present themselves as having a major role in our biosensor, and here you can see a scheme of our nanoparticles. So here in green we have the gold core, and presented with the dashes we have biotin molecules. These biotin molecules are going to bind to adalimumab. When they do so, according to the concentration of adalimumab presented in our sample, the whole size and shape of our nanoparticle will change. And so, as they bind, the solution absorbance will also change. We can later convert these changes in the absorption in a value of concentration for adalimumab. It is also important to point out that the solution of gold nanoparticles that we used had a concentration of 0.5 micrograms per milliliter.
So, how do we transduct the light signal into an electric one? We use a really simple setup. We use a 405 nanometer laser, photodiode as the detector, and this photodiode is connected through a simple amplification circuit to an Arduino board. This Arduino board is equipped with a Bluetooth module that allows the sync of the Arduino with the smartphone application. Additionally, we have a polyester cuvette that functions as the holder for our gold nanoparticle solution. So, how did we find the wavelength of our laser? We first did an absorption analysis of the gold nanoparticle solutions with and without adalimumab at this concentration up top. And we registered where it was most different, that it was in the range of 400 nanometer to 600 nanometer. After that, we went to the spectrophotometer and we made an analysis for 4 different wavelengths. We did some more wavelengths, but these are the ones displayed, and we figured that where we saw biggest difference in the absorption would be in the 405 nanometer laser. So we chose that laser as our light source for the biosensor. We additionally have our Android application. As my colleague said, it's way more than just an application. It allows to control the biosensor, the data acquisition part of it, and it stores the information that we received. So we can do user profiles and patient profiles for the user of the biosensor. Finally, we did a calibration curve. That's the beating heart of our biosensor. We did 15 non-sample concentrations of ADL. And then we registered the electric potential that would be in the Arduino board. And for concentrations over 5 microgram per milliliter and less than 9 microgram per milliliter, that's the therapeutical value that would be important to know. We have an uncertainty of 20% of the read value, which makes our biosensor for this range good option. So what do we bring to the table? We are a fast and cheap process to obtain adalimumab results. We have a really simple sample preparation and also a really simple setup to work with. It's based on a well-established technique, and the Android application allows our biosensor to be more than just a biosensor. Any questions? This is us, LxUS. Thank you.
Oh, thank you for your presentation. I just have a question about the setup of your detection strategy. You used gold nanoparticle of 60 nanometer. You mentioned this in the document. I'm not sure why the 60 nanometer was chosen.
Okay.
Number one. So let me ask you two more quick things. So, and then you have the gold nanoparticle with the polyethylene glycol 5000, and then terminated with biotin. And then you have the anti-ADL antibodies. If you can tell me why did you choose 60 nanometer gold nanoparticle, and then the setup leading to the detection of ADL in plasma.
Okay, so
You answered the first.
yeah,
answer the
exactly.
second.
So the 16 nanometer gold nanoparticle it was because we wanted a smaller nanoparticle, so that when the adalimumab would bind to the gold nanoparticle, it would amplify the effect of its binding to the gold nanoparticle in terms of absorption. So we wanted a small nanoparticle that could contain a lot of adalimumabs. In that was the reason. Obviously, we wanted to test with smaller sizes and with bigger sizes to see what would be the results, but unfortunately we didn't have the time to do that. But the other part?
Yeah, can you put in the nanoparticle scheme, please?
Yeah.
There, this part over here presents the PEG and the biotin. The biotin is the anti-antibody. So the biotin is the one binding to adalimumab and not to anti-adalimumab.
So biotin, I mean, so are the antibodies have streptavidin or something, or this? I mean,
sorry.
How come the biotin will bind to the anti-ADL?
Because they are an antibody for adalimumab.
That's correct, but what biotin has to do with this?
Biotin is an antibody for an antibody, so they will bind.
Okay.
Yeah.
So maybe you say something here.
Yeah.
But biotin, is that specific? Because biotin binds to streptavidins, to all kinds of things.
Yeah, that's true. But in our sample, we only have the plasma and adalimumab. If we had other antibodies, yeah, it probably could bind. But patients usually are not into the different medication for the same thing, and so we don't. Yeah.
So do you know the specificity? Have you tried to measure in with other antibodies in the sample?
No, we didn't.
No.
Only using adalimumab.
So I'm just trying to maybe pinpoint exactly the mechanism. So you mentioned absorbance, but gold particles absorb at 520 nanometers. Isn't it more a scattering assay where when you change the size of the particle, you see more scattering from the gold particle?
That's a really good point, because indeed the gold nanoparticles have the absorption at the 540 range. But the concept behind our biosensor is trying to detect changes. Changes are very important, and comparing it, our gold nanoparticle solution with our nanoparticle solution with adalimumab, if we always do it the same way, we try to patternized the error as further as we could do. So in this case, you can see in green the gold nanoparticle spectrum, and by yellow the gold nanoparticle spectrum and the adalimumab, which gave us this in red the biggest difference in the wavelength. But this was for 10 microgram per milliliter gold nanoparticle solution, and for adalimumab of 12. So we started to get better at doing the concentration. We reduced the size of the concentration of the gold nanoparticles to 0.5, and we figured that with the 405 nanometer laser, it was where we find the biggest difference, because as you can see in here, now with a gold nanoparticle solution of 1 microgram per milliliter, we see that this curve is where it's the biggest difference between the...
And can you explain why it goes back into higher absorption at the very low concentration?
Okay, this is a really good point, because what we think it happens in this situation is that since the adalimumab concentration is so low, what you're actually measuring is the other things that are in the solution, like the plasma and wherever. So for that point, our biosensor isn't that well prepared to take handle of those lower concentrations. So we focus in higher adalimumab concentrations where it would be more linear, the behavior of it.
Just to continue the question then, isn't it then a risk that you cannot identify lower volumes?
Lower volumes or lower concentration?
Lower concentrations. So
yes, if your question is right, it's a risk because lower concentrations we cannot detect it as we would want. But we had a lot of struggles with our biosensor and the time was on point. Then we thought, okay, let's try to do it best for the range that it would have an application for. And it was that range that I told you, 5 to 9 microgram per milliliter.
okay, and maybe another question. You showed the laser setup in one of the
Yes.
pictures here. Yeah.
Yeah.
What do you expect from a final setup? Is it can you make it much smaller or?
Okay.
How do you see the product should look like when you want to use it?
Definitely, we would try to get it smaller. The usage of a cuvette would not be ideal. We will find other solutions for it. But since for this prototype we wanted to keep it simple and cheap, like this, the whole biosensor was like 600 euros. So it was really, really cheap for what we are trying to do in here. And in further work, definitely trying to reduce the size of the biosensor as is. Try to use a microfluidic cartridges perhaps to do the nanoparticle solution. Try to use a different wavelength of the laser because, for example, one of the struggles that we had with time is that we could only test the wavelengths of the lasers that were available in our school for us to use. So that's why 405 was one of the options because it was what we had available.